Hello, and welcome to my video series of algorithms. This is part 5 of Module 4, focused on greedy algorithms. In this video, we will continue our discussion of the minimum spanning tree problem, or the MST problem. We are given a connected undirected graph with weighted edges, where no weights are negative. The goal is to find a set of edges that connect all nodes while minimizing the total weight. The MST problem can be solved using several greedy algorithms. In the previous video, we have discussed Prim's algorithm, Kruskal's algorithm, and the reverse delete algorithm. In this video, we will discuss their implementation details and analyze their time and space complexities. Let's first look at Prim's algorithm. Most parts of the pseudocode are straightforward, except for the highlighted one. Specifically, we need to select the edge with the minimum weight that connects an unvisited node. The scenario is illustrated by this figure, where nodes U are visited and V are unvisited. We need to find the minimum cost edge between them. This step is also in Dijkstra's algorithm for the shortest path problem. The only difference between Dijkstra's algorithm and Prim's algorithm is the object function they try to minimize. Specifically, for Dijkstra's algorithm, its object function includes both the accumulated path length for reaching the visiting node U and the edge length between U and V. However, Prim's algorithm only considers the edge weight. Despite this difference, the overall setup for both algorithms remains the same. We can still use the heap data structure for this step in Prim's algorithm. The heap data structure allows us to find the minimum in O log n time, where n is the number of elements in the heap. Due to the similarity with Dijkstra's algorithm, Prim's algorithm shares the same time and space complexity. Specifically, Prim's algorithm can run in O v plus e times log v time, where v and e are the sizes of the node set and the edge set respectively. It also needs O v plus e space. For more details, please review part 3 of this module. Now, let's look at Kruskal's algorithm. The key to implement this algorithm is determining whether the nodes U and V are in the same set. And we also need to merge two sets efficiently. For this purpose, we can use the union find data structure, which is also known as the disjoint set data structure. As the name suggests, this data structure supports two basic operations: union and find. The union operation takes two elements, x and y, as parameters, and merges the sets containing x and y. The find operation takes an element x as parameter and returns the set that contains x. Using the union find data structure, we can check whether U and V are in the same set by comparing find U with find V. We can also merge the two sets containing U and V using union UV. Now, let's briefly discuss how to implement the union find data structure. Consider the example we have here. We will use an array to store the set information for each node, which is shown in the top right corner of the slide. Initially, each node belongs to its own set. For example, the array shows that node A is in set 1, node B is in set 2, and so on. Note that the numbers like 1, 2, 3 represent set IDs, not array indexes. The find operation returns the set ID stored in the corresponding entry. The union operation relabels set IDs to merge two sets. For example, when merging the set containing A with the set containing B involves relabeling B's entry to 1. The updated array now means both A and B are contained in the set 1. When merging two sets with unequal sizes, we shall relabel the smaller set to save computation. For example, when merging the set containing B and the set containing C, we shall relabel the latter since it contains fewer elements. More importantly, if we always relabel the smaller set, the average time complexity for the union operation becomes O log n, where n is the number of elements. There are other ways to implement the union find data structure, which will lead to different time complexities for the union and find operations. If you are interested in those topics, you are encouraged to find more information online. Now, we have found time complexities for the key steps in the pseudocode. Since the union and find operations are performed within the for loop, so we need to multiply their time complexities with the number of iterations. Taken together, the time complexity of Kruskal's algorithm is OV plus E times log V, where V is the number of nodes and E is the number of edges in the graph. The space complexity is OV plus E, which is used to store the graph itself. Note that the union find data structure only needs an array of size V. Therefore, we will not increase the space complexity. You can pause here to go over the details if it's not obvious to you. Finally, let's look at the reverse delete algorithm, where we need to decide whether two nodes are still connected after removing an edge. To do so, we can use the breadth-first search or the depth-first search algorithms, which traverse the graph from one node and check if they can reach the second node. Both algorithms run in OV plus E time. We will not delve into their details, and you can find more information about them elsewhere. Now, we have found the time complexities for the key steps in the pseudocode for the reverse delete algorithm. As a result, the time complexity for the reverse delete algorithm is OE times V plus E. Its space complexity is OV plus E, which is used to store the graph. In summary, we have discussed the implementation details for Prim's algorithm, Kruskal's algorithm, and the reverse delete algorithm. The main idea for implementing Prim's algorithm is to use the heap data structure. For Kruskal's algorithm, we use the union find data structure. And for the reverse delete algorithm, we use the breadth-first search or the depth-first search algorithm. Prim's algorithm and Kruskal's algorithm have the same time complexity of OV plus E times log V, while the reverse delete algorithm has a slower time complexity of OE times V plus E. All of them have the same space complexity of OV plus E. In the next video, we will prove the correctness of these greedy algorithms. Thank you for watching and see you next time.